Imagine the smallest thing you can possibly think of. Now imagine something even smaller. That's the world of atoms, the building blocks of everything we see and are. In the early 20th century, scientists were just beginning to unlock the secrets of these tiny particles. They knew atoms existed, but their inner workings were a complete mystery. Physicists faced a puzzle. They had the laws of classical physics, which worked perfectly for large objects like planets and apples. But these laws seemed to break down when applied to the microscopic realm of atoms. It was like there was a whole different set of rules governing the universe at the smallest scales. The atom, according to the prevailing model, resembled a miniature solar system, a dense nucleus at the center containing positively charged protons was orbited by negatively charged electrons. This model, while a good starting point, couldn't explain some of the strange behaviors observed in atoms. In 1913, a young Danish physicist named Niels Bohr stepped onto the scene. Bohr was working in Ernest Rutherford's laboratory in England, a hotbed of atomic research. He was fascinated by the puzzle of the atom and was determined to find a solution that reconciled classical physics with the new and perplexing quantum theory. Bohr had a brilliant idea, a flash of insight that would revolutionize our understanding of the atom. He proposed a radical new model, one that incorporated elements of quantum mechanics, a revolutionary theory that was just beginning to emerge. This theory suggested that energy, unlike in classical physics, wasn't continuous, but came in discrete packets called quanta. Bohr's model was as elegant as it was groundbreaking. He imagined electrons not simply as tiny planets orbiting the nucleus, but as occupying specific quantized energy levels. These energy levels were like rungs on a ladder, with electrons only allowed to exist on a rung, not in between. Bohr's model was nothing short of revolutionary. It challenged the very foundations of classical physics, which assumed that electrons, like planets, could orbit at any distance from the nucleus. Bohr's quantized orbits meant that electrons were restricted to specific energy levels. This radical concept explained why atoms, when excited, emitted light at specific wavelengths, a phenomenon that had puzzled scientists for years. When an electron absorbed energy, it jumped to a higher energy level. When it fell back down to a lower level, it released that energy as a photon of light, with the wavelength of the light determined by the energy difference between the levels. This simple yet profound idea explained the unique spectral lines observed when light from different elements was passed through a prism. Each element, with its unique arrangement of electrons and energy levels, produced a characteristic pattern of spectral lines, like a fingerprint. Spectra, the fingerprint of atoms. One of the most compelling pieces of evidence supporting Bohr's model came from spectroscopy. Scientists had long known that when light from a heated element was passed through a prism, it produced a unique pattern of colored lines, called a spectrum. These spectral lines were like fingerprints, unique to each element. Bohr's model elegantly explained this phenomenon. The spectral lines corresponded to the specific wavelengths of light emitted when electrons in an atom made quantum jumps between energy levels. Each element, with its specific number of protons and electrons, had a unique set of energy levels. The spectral lines were a direct consequence of these quantized energy levels, providing strong experimental support for Bohr's model. Section 6. Bridging the gap. Classical and quantum. Bohr's model was a remarkable achievement. It successfully bridged the gap between classical physics and the emerging quantum theory. It incorporated elements of both, providing a framework for understanding the behavior of atoms at the quantum level. The model retained the classical idea of electrons orbiting a nucleus, like planets around a star, but it introduced the revolutionary concept of quantized energy levels, a hallmark of quantum mechanics. This blending of classical and quantum concepts was a testament to Bohr's genius. He recognized the limitations of classical physics in the atomic realm while embracing the explanatory power of quantum theory. The limits of Bohr's model. As successful as it was, Bohr's model was not without its limitations. It worked beautifully for hydrogen, the simplest atom, with its single electron. However, the model struggled to accurately predict the spectra of more complex atoms with multiple electrons. The model also failed to explain why some spectral lines were brighter than others, suggesting that some transitions between energy levels were more probable than others. And it couldn't account for the fine structure of spectral lines, tiny variations in wavelength that hinted at a more complex picture. These limitations didn't diminish the significance of Bohr's contribution. His model was a crucial stepping stone, paving the way for the development of a more complete and sophisticated theory of quantum mechanics. Beyond Bohr. The evolving atom. Bohr's model, while groundbreaking, was just the beginning. It was a stepping stone to a deeper, more nuanced understanding of the atom. Scientists soon realized that electrons weren't just tiny particles whizzing around a nucleus in neat, predictable orbits. Quantum mechanics revealed that electrons behave more like waves than particles, their positions and momenta governed by probabilities rather than precise trajectories. The neat, planetary orbits of Bohr's model gave way to a fuzzier, more probabilistic picture of the atom, with electrons smeared out in clouds of probability. This new quantum picture of the atom was far stranger and more counterintuitive than anything classical physics could have predicted. Yet, it provided a more accurate and complete description of the atomic world, explaining the limitations of Bohr's model and ushering in a new era of atomic physics. The quantum world, a realm of uncertainty. The development of quantum mechanics revealed a universe far stranger and more counterintuitive than anything classical physics could have envisioned. At the atomic level, the deterministic, clockwork universe of Newton gave way to a realm of probabilities and uncertainties. Electrons, it turned out, didn't follow predictable paths like planets orbiting a star. Instead, their behavior was governed by wave functions, mathematical expressions that describe the probability of finding an electron in a particular location at a particular time. This inherent uncertainty wasn't a limitation of our measuring devices. It was a fundamental aspect of the quantum world, a world where particles could exist in multiple states simultaneously, where the act of observation could alter the state of a system. The enduring legacy of Bohr's model. Niels Bohr's model of the atom, though superseded by more sophisticated models, remains a cornerstone of atomic physics. It was a pivotal step in our understanding of the atom, a bridge between the familiar world of classical physics and the strange and wonderful realm of quantum mechanics. Bohr's model taught us that the rules governing the universe at the atomic level were fundamentally different from those we observe in our everyday lives. It introduced the world to the concept of quantized energy levels, a concept that underpins our understanding of everything from lasers to semiconductors. More importantly, Bohr's model inspired a generation of physicists to delve deeper into the quantum world, leading to the development of quantum mechanics, one of the most successful and profound scientific theories of all time. A universe of mysteries. As we've journeyed into the heart of the atom, we've encountered a universe far stranger and more mysterious than we could have imagined. A universe where energy is quantized, where particles behave like waves, and where uncertainty reigns supreme. Bohr's model, a brilliant fusion of classical and quantum concepts, was a crucial step in this journey of discovery. It opened our eyes to the quantum world, a world that continues to challenge our intuitions and expand our understanding of the universe. As we gaze out at the vast expanse of the cosmos, filled with stars, galaxies, and endless possibilities, we are reminded that the universe is full of mysteries waiting to be unraveled.